Hey, welcome back! Today we'll talk about Google's Guide to App Architecture, a detailed recommendation on how to design mobile apps. It was created for Android, but surprisingly it has been getting popular among iOS engineers as well, especially in the context of system design interviews. It emphasizes patterns like unidirectional data flow and single source of truth. So today we'll do a high-level overview of this guide, its core architectural principles, and answer the question, is this architecture a good choice for mobile system design interview? Okay, so why do mobile apps need architecture at all? I'll give you 4 reasons. First, it helps with growing complexity. As your apps adds more and more features, a clear architecture stops the code from turning into a big mess. Second, maintainability. When responsibilities are clearly separated and patterns are consistent, making changes becomes safer, bugs are easier to fix, and long-term development is just cheaper. Okay, third, testability. A modular design lets you test parts of the app or certain components in isolation, and mocking dependencies becomes straightforward. And finally, team scalability. Architecture gives everyone sort of a shared language, which lets multiple engineers work in parallel without stepping on each other. Now, let's do a high-level overview of Google's Guide to App Architecture. Interestingly, they don't mention this in the guide, but I would say it's highly influenced by the ideas of clean architecture. Also, important moment, it works so much better for declarative UI frameworks, such as Jetpack Compose and Swift UI, so Google recommends using at least 2 layers for your mobile application. A UI layer that is responsible for displaying data on the screen, and a data layer that contains business logic and exposes application data. Additionally, for more complex apps, you can add a domain layer in between those to simplify and reuse the interactions between the UI and data layer. Because of that, you can see that the domain layer is marked as optional on the diagram. So the key idea here is to separate out how data is shown, how it is processed, and where it comes from. So let's go now layer by layer and discuss their responsibilities and common components. First is the UI layer. Its role is to display data on the screen and update whenever it changes, either from user actions or external inputs like network responses. It has 2 main parts: UI elements that render data and stakeholders, such as view models that hold data, expose it to the UI, and handle presentation logic like formatting the data or preparing data for display. In practice, the UI observes state and sends events or intents back to the view model. Next is the data layer. The data layer is where your app business logic lives. It defines how data is created, stored, and updated. The core building block of the data layer is the thing called repository. Repositories are responsible for providing data to the rest of the app, centralizing changes to the data, and resolving conflicts between multiple data sources. Usually you'll have one repository per data type, for example, user repository, news repository, and so on. A repository can work with one or multiple data sources and decide how to combine or prioritize them. Each data source works with only one source of data, which can be a network source, a local database, or just a file. These data sources handle the low-level details of reading and writing data, while the repository sits above them and contains the business rules. Okay, next up is the domain layer. It's an optional layer between the UI and data layers. You want to introduce the domain layer when you have complex business logic that involves working with multiple repositories, or when that logic is reused by multiple view models. Classes in the domain layer are commonly called use cases or interactors. Each use case should have a single responsibility. For example, your app could have a get latest news with authors use case, which pulls, combines, and transforms data from 2 separate repositories: news repository and authors repository. So that means use the domain layer only when needed to handle complexity or add some sort of reusability, because you don't need it for small and simple apps. Now, let's talk about common architecture principles emphasized in Google's Guide to App Architecture. The first one, really important, is separation of concerns. To put it simply, it is about keeping UI logic separate from the rest of the code. Instead of putting everything into the UI layer, each component should focus on single responsibility. UI classes should only handle what they're meant to do, displaying content and responding to user actions. By separating responsibilities across our components, the code becomes cleaner and easier. It also makes testing simpler, since each component can be verified in isolation. Next, immutable data models are objects that cannot be changed after they are created. In mobile apps, this often includes DTOs, or data transfer objects, which carry data between layers without any behavior. Once a DTO is created, its state stays the same and any updates produce a new instance rather than modifying the old one. This reduces unexpected side effects, makes the app's behavior more predictable, and simplifies debugging and testing, especially in reactive or multi-threaded environments. Next one, single source of truth, means that each type of data in your app has just one owner, the only place where it can be modified. The single source of truth exposes the data as immutable, and any updates happen through functions or events provided by the owner. This keeps all changes centralized, prevents other parts of the app from accidentally modifying the data, and makes bugs easier to track. So where is the single source of truth? In mobile apps, the ultimate single source of truth for persisted app data is the database. A view model is the single source of truth for the UI state relevant to each specific screen. And for remote data system level, the server obviously is the single source of truth, so local caches must be synchronized properly. Okay, next one, unidirectional data flow. It is a pattern that makes the movement of data in the app predictable by enforcing a single direction for state changes. Data flows from a source, such as a database or a view model, through the app's layers, usually ending at the UI. Any changes to the data happen by sending events back toward the source, which then updates the state and exposes it again as immutable. So there is this one-way flow of data that keeps data consistent, reduces bugs, and makes it easier to understand how changes propagate through the app. It works really close with our single source of truth pattern, ensuring all updates happen in a controlled, traceable way. Okay, cool. Now we've covered the main part of Google's Guide to App Architecture. Let's answer the question: is this approach acceptable for a mobile system design interview for Android and iOS devs? And the answer is a solid yes. First of all, this guide is highly influenced by the clean architecture ideas. It follows a similar structure and breaks down responsibilities clearly, so it's a really good approach you can use. Second, patterns like unidirectional data flow work really well with modern mobile development stacks such as SwiftUI, Compose, and reactive programming. For iOS developers, the naming of components such as use cases and repositories might be something new. Historically, more common iOS style naming was services or interactors, but I would say it's still a good approach to use for your app architecture. In interviews, generally what matters is not how you name components, but explaining clear boundaries between them, the data flow, and responsibility separation. Alright, if you want to read deeper, check out the link to the source material in the video description. By the way, let me know in the comments what you think about the new format with my webcam shown in a circle, and don't forget to like and subscribe. Thanks, and see you in the next one.